Bonjour à tous. Hello everyone. Very happy to be here today to introduce the speakers. So first, let's talk about event-driven architectures. They have many use cases in web development and especially in serverless. They are great for building a web application, but they are very painful when it comes to refactoring and changing your data models. Well, not anymore, because the first AWS serverless heroes speaking today will tell us about the best practices and the rules to deal with event-driven architectures. He is a 12-time certified AWS engineer. He comes from Netherlands. Let's give a warm welcome to Luc.
Thank you, Pierre, for the introduction. I have to keep up this energy. So let's start. The Tao of Event-Driven Architectures. The literal meaning of Tao in Chinese is the path or the way. And in that sense, today's talk can be seen as a set of guidelines to build your mature event-driven architectures. In a more philosophical sense, Tao roughly means the flow of the universe, or some essence that keeps the universe balanced and ordered. And that's the second layer of today's talk. By following the 10 simple rules covered today, you will find a natural balance and structure in your event-driven architectures. Sorry guys, you switched again. My name is Luc van Donkersgoed. I'm a lead engineer at PostNL and AWS Serverless Hero. PostNL delivers an average of 1.2 million parcels per day. And this is powered by an entirely event-driven landscape. So we literally process billions of events per month in AWS. And today's talk is about how we found our happy path in event-driven architectures. The reason you're here, the reason you want to listen to this story, is that you need guidelines to succeed in growing and evolving your event-driven architectures. If you don't use guidelines, your event-driven landscape will devolve in a chaotic mess. And this is a natural result of how most event-driven architectures organically grow. They start out with a few interconnected services, exchanging data in a way that is locally optimized. One service talking to another, then we add one more, add another, and they exchange data in a way that works exactly for these exact services. But as you add more services and nodes to your architecture, or even when you start to exchange events across entirely different services and domains, structure is often lost. The event integrations might use different formats, different languages, different types of encoding and compression, and so on. And at some point, serenity and calm are not quite the words you associate with your architecture anymore. In fact, you might find that operational incidents are hard to investigate and understand. You might look up against the task of adding, changing, or removing a service in your landscape. And you might not even know what the effects of a change are, where a supposedly safe event mutation leads to downstream incidents. Today, I will tell you about 10 simple rules to keep in mind when designing, growing, and refactoring your event-driven architectures. The rules are divided into 3 sections. First, we'll talk about event design, followed by communicating and evolving your events. And the final part will be about integrating your events in a larger landscape. And these rules will keep your event-driven architecture well organized and maintainable. And through this, your developers will work with predictable, manageable events, which allows them to focus at the business problems to solve. So let's start with the first rule. Use JSON for all of your events. And this might sound like an overly opinionated rule, but it forms the foundation of a predictable and well-maintainable event-driven architecture, as we'll see in many of the other rules. And when I say use JSON everywhere, I explicitly mean don't use any other language anywhere. Don't use XML, don't use YAML, don't use plain text, don't use any other format. And to clarify why, let's take a look at a few of the other options. First, XML. Well, actually, I'm not even going to go there. Don't use XML. We don't live in the 90s anymore. Next, YAML. And YAML might seem like a valid candidate for some use cases. However, YAML is built for humans. It is not natively supported by almost every language like JSON is, and most importantly, it is not natively parsable by many cloud services. For example, Amazon SQS, SNS, and EventBridge can natively apply powerful filtering and routing rules on JSON payloads, but not on YAML. And that is also the reason why we don't use Avro or Protobuf. Although these are very efficient and powerful formats, they don't integrate well in the native AWS service landscape. And in practice, we found that we don't even need the efficiencies of these formats. Even at billions of events per month, JSON works just fine. And then there's plain text. And this one deserves a bit of additional attention. So let's say you have two systems exchanging events. The first system detects an object, a parcel, for example, and sends out an event that notifies another system of the weight of the object. Event that says weight 12. Now, System B needs to parse this event, which is a bit cumbersome. And since System B already knows all the context of this event, after all, it is sent by the weight detector system, the two systems simply agree to drop the keyword. And this is very efficient, right? And this is an example of a locally optimized system. However, the problem lies in the evolvability of this system. If System A is upgraded and is suddenly also able to detect the width and the height of the object, how can that data be added to this event? Now, you could do something like this, but this is impossible to understand and evolve over time. What do these values mean? What happens if any of these values is missing? Instead, use JSON. The meaning of the values is immediately clear. The event can be parsed by any system, and the event is evolvable simply by adding more fields as needed. And even better is to add the unit to the keyword so there can be no ambiguity about the meaning of those values. So we've established that we should use JSON everywhere. Rule number 2 further improves on this guideline by adding a standard event envelope. An envelope is something that you wrap around a message. And an event envelope is no different. It's simply a wrapper around your original message. And one format that has seen a lot of success is the metadata data envelope. I think the creator of this event is in the room, so you might want to talk to him later. In this envelope form, the data object contains your original actual event data, like the height and weight that we saw earlier. The metadata key allows us to add additional information about the event itself. So this can be the time at which the event was generated, the type of event, the version of the event, and much more. And using a standard envelope with predefined keys for all of your events makes investigating and understanding operational incidents significantly easier. And it also allows consumers of your events to apply advanced processing, such as filtering, in a standardized way. Now, the third rule builds upon the metadata envelope. And the rule is to add a unique event ID to the metadata of each and every event. And I cannot stress strongly enough how important this rule is. If you have one takeaway from the talk, let it be this. Have your producers generate unique identifiers and add them to the metadata of your events. In practice, this is really easy to achieve. The producers, at the time they're trying or attempting to send out an event, generate a unique identifier, like a UUID. They add it to the metadata section of the event, and now all of our systems have a reliable way of tracking an event, regardless of the underlying technology used. We can use this event ID to build observability traces, to apply the storage first pattern, to guarantee item potency, and more. And we'll cover more of these topics later in the talk. The fourth rule that helps achieve serenity in your event-driven architectures is to use schemas and contracts. Schemas define the structure of your events, including which fields are mandatory, which fields are optional, the data type of the fields, and even the ranges and enumerations of their values. So this is an example snippet of a JSON schema. And this example defines the structure of the metadata key that we saw earlier. So let's go through it line by line. The top line indicates that this schema applies to the metadata key. The second line indicates that that key will always contain an object. And the third part specifies the values and the properties of that object. And then the final line specifies that the event version key should always be present within that object. Now, schemas are used to clearly define what data will be sent by a producer. And this is important for a number of reasons. First, it allows consumers to build their systems based on the contract even before data is being produced. And second, it allows producers to evolve their systems, their events safely, as long as they adhere to the contract. So in other words, as long as the producer does not break the contract, they cannot create downstream incidents. So this brings up an interesting question. How do you evolve your events safely while adhering to the contract? After all, your application landscape is never static. New data, new insights will become available over time, requiring you to update your events. So how to evolve your events safely is answered by the fifth rule, and it is to maintain backward compatibility. But there are two parts to this rule. The first part relates to non-breaking changes. These are mainly additions to your events, like adding fields to an existing event. And this should always be allowed. And it generally follows what's known as Postel's law. Be conservative in what you send, be liberal in what you accept. So if a producer updates their events to include more data, that should never affect downstream consumers. The second part relates to breaking changes. And these are the kind of changes that will impact a downstream system, such as removing a required field or changing the data type of a field, for example, from a string to an integer. And a producer can never make these changes without involving their consumers. Now, the correct solution for breaking changes is to use event versioning. So let's take a look at an example. Let's say the system A sends out an event, and this event is called version 1. They have defined a contract, and the system B consumes that event, expecting it to match that contract. Now, the producer wants to break this contract, so they need to publish an entirely new version of this event called V2. Then they need to ask the consumer to migrate to that next version. In other words, they need to ask their consumers to agree to a new contract. And only when all consumers have accepted that contract and have migrated to the new version can the producer stop sending the initial version. And following these principles about versioning and backward compatibility are good protections against unforeseen compatibility issues. And as such, they help developers preventing from breaking production, which is a good thing if you want to achieve serenity in your event-driven architectures. The sixth rule is to maintain a schema registry. A schema registry offers a good way for producers and consumers to communicate about their events. So a schema registry is an online accessible repository that contains an overview of all the events in your system. It allows producers to annotate and describe their events, and it allows consumers to discover what events are available, their definitions, and their history. The schema registry is an essential component for stable event-driven architectures. It gives developers ease of mind because they can find all documentation about their events in a single source. But it only works if it's used as a single source of truth. So producers must send out events that match the definitions in their schema registry, or you're guaranteed to be off the happy path real quick. And that brings us to rule number 7, which is to use an event broker. As you're building and evolving your event-driven architectures, you're probably starting out with direct integrations. However, as your landscape grows, you'll soon find that this approach becomes unmaintainable. Additionally, a mesh architecture like that makes the versioning and backwards compatibility and the schemas and contracts that we discussed earlier very difficult to implement. So instead, we use an event broker. In essence, an event broker allows a landscape with direct integrations like this to evolve to a more star-shaped landscape like this. And in this design, the producers are truly decoupled from their consumers, at least in a technical sense. And if a new consumer needs access to an existing event, they simply subscribe to that event on the event broker. And now you can see how important contracts have become, since producers might not even know who their consumers are anymore. The entire landscape has become dynamic, ever-changing. Now, to make optimal use of an event broker, it should combine functionality with the schema registry, because this will allow the consumers to discover which events are available on the event broker. And additionally, the event broker should validate events against their schemas, against their contracts, before they are being accepted onto the event broker, because this protects downstream consumers against malformed or breaking events. Now, in a mature event-driven architecture, you should also be able to query which consumers are subscribed to specific events and event types and event versions, because this will allow producers to determine which event versions can be deprecated and maybe even deleted. And so we've arrived at rule number 8, which is to use event supporting APIs. And this rule needs a bit of background. So events generally tell a fact about a given entity. So in this example, the entities are a bike, an order, and an invoice. And the facts being told about these entities are that they are returned, created, and paid. The event will also contain some additional details. So for example, in the bike returned event, this might be the identifier of the bike, the location at which it was returned, and the date and the time at which it was returned. And it is up to the producing system to determine which details they want to include in their events. But it will always be a limited set of details, not every single detail known about this entity. For example, adding the color of the bike does not make much sense for a bike returned event. However, some downstream system might want to know the color of the bike being returned. And they can ask the producer system to add that value to the event. But adding this field might break the design or the scope of the event. And also, where does this end? Because other systems might want to know additional details, like the brand of the bikes being returned or the age of the bike being returned. And simply adding every detail simply because consumers ask for it does not help to achieve serenity. Instead, the producer should send out the data that they believe is applicable to the majority of their consumers, and they should make sure that they include some sort of entity ID. At the same time, they should host a resource API that allows downstream consumers to fetch additional details about this entity using the entity ID. So a GraphQL-based API, for example, could be a good fit. But of course, there's a natural tension between event-driven architectures and resource-based APIs. After all, one of the major benefits of event-driven architectures is that scaling up to millions of consumers hardly requires more compute capacity than a single consumer would. But when all of those millions of consumers start to call back your API and request additional resources, your API might quickly become overloaded. And producers need to be aware of this balance, and they need to evolve their events based on usage patterns. Now, the rule of thumb is to start by including the relevant details and include an entity ID. Then you monitor your request-based APIs and you find out which fields are often requested. Then you evolve your events based on these patterns and you work with your consumers to reduce the load on your APIs. And again, GraphQL might be a good fit because it allows you to monitor exactly which fields are being requested. Now, there are a few exceptions to this rule. For example, expiring data should generally not be included in an event. This might be a frequently changing value, like a stock or a balance. And consumers are usually better off fetching the latest state of that value in an API than relying on the contents of an event. And so, we're approaching the end of the list. Many of the rules that we covered before were aimed at the producer of events. Rule number 9, to use the storage first pattern, is more aimed at the consumer side of things. So when a consumer receives an event, they can generally do two things. Either they process the event immediately, take action on it, fulfill some sort of process, and only report success to the sender of that event when the process has successfully completed. Or they process the message asynchronously, which means that they immediately respond that they have received the event, and then process it in their own time. In a high volume, low latency, event-driven architecture, slow consumers can lead to upstream incidents. For example, queues might back up, latency might increase, memory buffers might fill up, or a producing system might experience increased concurrency. To prevent these issues, consumers should accept and acknowledge events as soon as they can. So they should apply the asynchronous message processing pattern. And this can be achieved by immediately storing the events in a queue or a database. And this is called the storage first pattern. Now, using the storage first pattern has additional benefits. For example, it allows consumers to deduplicate messages that might inadvertently have been sent more than once because of network issues or scaling failures. And in this scenario, the unique event ID that we sent with our metadata really comes into play. Because now the consumer can use this event ID as a unique identifier, a unique key in their storage system, and simply choose to drop the message immediately if it is received a second time. The storage first pattern also allows for an easy platform to achieve idempotency. So if a user performs an operation multiple times, the receiving system can simply see if the request has already been processed in their storage system and choose to ignore the second request or return in progress or success immediately. And that brings us to the last rule in the set of 10. And the last rule combines two of my favorite topics, which are events and observability. And rule number 10 is to trace your events. So let's discuss why tracing is important. In a large distributed landscape, it can be very difficult to observe what is actually happening. For example, it is hard to understand which upstream events lead to which downstream events, which consumers are subscribed to which producers, what the root causes of operational incidents are, and which systems introduce latency in your landscape. Now, the solution is to use distributed tracing, which allows downstream consumers to continue a trace that started in an upstream system. So let's take a look at what this means in practice. Our example architecture looks like this. System A finishes a bike rental, and when they do, they send out a bike returned event. This is received by system B, which sends out an invoice, and when it has sent out that invoice, it sends out an invoice sent event. This is received by system C, which updates the user's credits. Now, if each of these services emit telemetry, then each of their processes can be considered what is called a span. Literally, a span of time spent on a specific task. But without distributed tracing, these spans will live as individual sets of data. There's no connection between them. There's no cohesive whole. And we can use the metadata section in our event envelope again to add these connections between the spans. For example, we can use the trace parent key to include the identifiers of the span that emitted the event. And the downstream system can then create their own child spans from this parent span. Now, the result is that you gain deep insight into the relationships and subscriptions in your event-driven architecture, including any unexpected patterns, volumes, or latencies. And of course, the more complex your system becomes, the more benefit you will experience from these insights. Having a waterfall chart like this one will be an enormous time saver when an operational incident occurs, which again helps to achieve peace of mind. And that brings us to the end of the presentation. We've covered 10 simple rules to achieve serenity in your event-driven architectures. So let's quickly recap 10 points. First, we talked about event design, and we talked about using Json, adding an event envelope, and using a unique event identifier. Then we talked about communicating and evolving your events, and the rules were to use schemas and contracts, to main backward compatibility and use versioning if you can't, and to use a schema registry. And in the final part, we talked about integrating and supporting your events in a larger landscape. We talked about using an event broker, supporting your events with resource APIs, using the storage first pattern, and to trace your events. But all of this is just a set of guidelines. What is the overarching theme? What is the main takeaway from today's talk? It's this. Events are always part of a larger, evolving system. And you should always design your events for that system, not just for the local services that produce those events. I hope today's talk will help you evolve and grow your event-driven architectures. And remember, follow the path, achieve serenity. Thank you.
Thank you very much, Luke. Very insightful. I think many of us would have benefited from knowing these rules before getting into event-driven architecture. Now we can go to questions. So if any of you have any question, I can give you the mic. Yes.
Hi. Thanks for your speech. Very interesting. So you talked about nature growing in a chaotic way at the beginning, and then the path to achieve serenity. So once your infrastructure is built on a chaotic way, how do you switch to a more serene path? Do you have to start from scratch all over again?
I'm not sure if I understood the question entirely. Sorry, I couldn't hear exactly. So what was the question exactly?
Okay, sorry. Once you have built your infrastructure in a chaotic way, and you need to switch to a...
In what, sorry?
In a chaotic.
Okay, yeah.
Chaotic way, and you need to switch to what you have described with your 10 principles.
Yeah.
So how do you do it?
Okay.
Do you have to start from scratch and build everything all over again?
Okay, thank you for the question. So the question is, if you have a chaotic architecture and everything is just sending data and there's no structure, how do you evolve from that into a more, let's say, serene architecture? So you definitely don't need a big rewrite. You can just start anywhere. The beauty about events is that you can send out whatever you use to send out, and also send out a well-structured, well-defined, evolvable event, and have them in parallel. So you could say that the initial version is like your version 0, and you then introduce a version 1. And then you can ask your producers to switch to that new structured, your consumers to switch to that new well-structured event. And only when they have all migrated there, which might take a bit of time and effort, then you can turn off version 0. And you can do that for all of your events. And if you introduce an event broker in the middle, like Amazon Event Bridge, you can just start sending your events there, decouple your landscape that way. And then at some point, everything has been migrated and you have your well-structured event.
We can take one other question, maybe.
Hello, thank you for your talk. I have a question about security and integrity of message. because in real world we need security. And what is your recommendation to be sure that this event was produced by this consumer and not by an account directly inject in event bus?
Yeah, that's a good question. So there's always the question about trust and security. So at PostNL, we've actually expanded on the patterns that you've seen here quite significantly. So there's no easy answer, but there's a few things that you can do. One is to have some sort of system in place that makes sure that only trusted actors can produce events on your event bus. We actually do validation before that. So we have Lambda functions validating that events come from the right place before we put them on the central event bus. But that, of course, it's always a balance and a trade-off because it takes a lot more time. It's more complex to build. And the same goes at the consumer end. Like, you might want every one of your consumers to be able to receive all of your events, but some of them might contain sensitive data. So you might want some extra process to make sure that only trusted and allowed actors are allowed to create subscriptions on those events and not just receive everything. And the last thing that I would add is if you want your events to be public, but maybe certain fields, certain data, you don't want that to be public, like personally identifiable information or financial information, you could encrypt those specific fields, for example, with a KMS, and then the producer owns the KMS key, and they just send those events out publicly, and then they can provide access to that KMS key only to trusted actors. So the event is public, but those fields can only be decrypted by trusted parties. So there are solutions in place, but they're all complex. Right, thank you.
Thank you very much again.